Okay, so then let's start the lecture 2 of Fundamentals of OCT. And second installment of this lecture is lecture 2, Implementation of OCT. So here in this lecture, I'm going to give something like a details of the implementation of the OCT, which includes the rescaling from the detection domain to K domain. This is one topic of today. And also I'm going to talk about the interferometers. The OCT is a low coherence interferometry, so it's surely we need interferometers. But there are several types of interferometers, and we need to properly select it. And I'm going to give you some guidelines for the proper selection of the interferometer today. Okay, and then let me start. The first topic of today is rescaling. We call it as a K-linear calibration and rescaling. Okay, the rescaling process can be split into two. Okay, the first process is a K-linear calibration, and this includes the calibration of the spectrometer. For example, when you take the signal with the spectrometer, normally the signal is linear in lambda wavelength. But to Fourier transform it, it should be linear in frequency. Okay, the frequency is inverse. The frequency is proportional to inverse of lambda. So it has no linear relationship. So if you apply the Fourier transform to the lambda domain signal, you are going to have a broadening of the signal, of the spectrum, unnecessary broadening of the spectrum. It results in a blurring of the image, OCT image. So first, after taking the original signal or raw signal, we need to remap it into the K domain before Fourier transform. It is so-called as a rescaling. And rescaling is, as I said, can be split into two processes, the calibration and rescaling. Okay, the narrow sense of the rescaling. Okay, so but before talking about it, let me clarify the problem we are going to tackle. And also, I would like to give a little bit short summary of last lecture. So here it's an optical scheme of Fourier domain OCD. Maybe some of you, especially some of you guys here in person, might know about it. But let me clarify. The Fourier domain OCD is a combination of the low coherence interferometer and the high-speed spectrometer. Or say, in narrow sense, the spectral domain OCD is a combination of low coherence interferometer and high-speed spectrometer. Okay, the light is a broadband light source, and it impinges the fiber interferometer typically, and then illuminate the sample. The light is dark scattered or reflected back from the sample, and then going back to the coupler. The other portion of the light is led to the reference arm and reflected back by the reference mirror, and then combined with the probing again with the coupler, and introduced into the high-speed spectrometer. Okay. And then the light, these two lights interfere to each other in a spectral domain after the say resolution into its spectrum by using a spectrometer. So we are going to have the interference fringe here, but it's not in a time domain, but it's in a normally wavelength domain. Okay, it's not exactly linear to the wavelength, but surely this is not linear in K. Okay, it's a little bit skewed, and that is something we want to correct. And it's the first topic of today's lecture. Okay, and then after taking the interference signal, we are going to apply the signal processing. Normally, it is a Fourier transform. I've already explained it last time. And then we have one-dimensional depth resolved signal. That is the OCT signal, right? And for this, we don't need to move the reference arm. That was necessary. That had been necessary for time domain OCT, but it is no longer required for the Fourier domain OCT, including the sweep source and the spectral domain. Okay, and then by applying one-dimensional transversal scanning by the rotation mirror, we call it as a B scan. we are going to have the two-dimensional cross-section. In short, for the Fourier domain OCT, a Fourier domain OCT requires only one-dimensional mechanical scan to take a two-dimensional image. This is one point. And if you apply the two-dimensional transversal scan by using two-axis Galvo scanner, we are going to have a three-dimensional body. Okay, that was actually the great advantage of the Fourier domain OCT in comparison to time domain OCT. Okay. Then a bit of mathematics, and it is actually the basement of today's first talk, the first portion of the rescaling. But anyway, let me explain. Sorry, I actually have already explained about it last time, but let me recapitulate it. Okay, here is the interference signal we are going to obtain by the CCD camera. But to simplify the situation, I wrote it as a function of k vector, wave number. But as I've already explained, in reality, what we are going to obtain is a signal which is a function of lambda or some little bit strange function. So this means the signal itself is in portion it's stretched and in portion they expanded. A stretch or shrink, okay, it's skewed. But anyway, we assume we are going to have this kind of signal. Maybe actually this signal is a signal we can obtain after the rescaling. But forget about it now. I'm just talking about the basic principle of Fourier domain OCT. Okay, here is the interference signal intensity or light intensity I of k, and it has three terms. The first term is reference intensity term, okay? And the fourth term is the probe intensity term. And actually, these two terms are going away after the OCT processing, so you can forget about it. And what's going to be happening with these two terms, if you're interested in, you can check the video of the past lecture. I think I've already talked about it. But anyway, the important term is this third term. It's a cosine term, and the phase of the cosine is k times, k is a wave number, times 2 constant, times the depth location of the sample, Gn. Okay, so this means if you think k is a variable, the frequency of this cosine term is Zn. It is the depth location of the sample. Okay, normally k, wave number, is treated as a frequency. But we just swap the point of view. K is now the variable. But the signal along k is modulated by the frequency of Cm. And Cm is the depth location of the sample. Means if we can apply the frequency analysis to this term, we can extract this Vn, the depth location of the sample. Higher the frequency, higher the depth, right? And the lower the frequency, the lower the depth. So then what's going to be happening, or what we need to do to extract the depth result image? That is actually quite easy. Applying the Fourier transform. And numerically, typically, we apply the fast Fourier transform algorithm. Okay, numerically. Then we are going to have some signal after the Fourier transform, and we are going to have some, say, like a peak. And the location of the peak after the Fourier transform indicates the location of Cn. Okay, you can imagine there is some cosine function, right? And applying the Fourier transform, and might have a single peak. And by touching with a maybe OCT system, and this cosine term becomes a high frequency or low frequency. If it becomes a high frequency, this peak after the Fourier transform moving to the deep direction. Okay, and if the cosine term becomes say coarse or low frequency, this signal comes close to 0 point. Okay, and actually it can working around. That is a very basic of the OCT. Okay, this is and actually this equation today we are going to heavily use. Please remind it. Okay, then the rescaling problem identification, problem definition. The issue with the original spectrum, what we call it as the raw spectrum, is not linear in K, but linear in lambda, most of the cases of the FD-OCT, or linear in something like a strange nonlinear function in the case of swept source OCT. But anyway, the important point is it's not linear in K. But to properly apply the Fourier transform, we need to make it as linear in K. Okay, so as far as it is linear in K, the signal is linear in K. Simply, we can apply the Fourier transform. Okay, if the signal is detected linear in K, what we can obtain is this guy. And once we have this, what we need to do is quite simple. Applying the Fourier transform. But normally, this is not the raw signal we obtain is not linear in K. So we need to make it into linear in K. That's the interpolation. Sorry, the rescaling. But for this, okay, sorry. I skipped something. Okay, so then what the issue? The spectrum, raw spectrum is not linear in K. So what we need to do is first calibrate the spectrometer or wavelength sweeping laser of the swept source OCT. The spectrometer is for FD-OCT, and the wavelength sweeping calibration is for the swept source OCT. But anyway, the mathematically it's quite similar. You don't need to say rigorously distinguish between these two. Okay, but maybe in this lecture, I'm normally say focusing on a spectral domain OCT. So you can think of it's a calculation of the spectrometer. Okay. So then after the calibration of the spectrometer means to define or find out the relationship between the pixel index and the K. Okay. So which pixel corresponds to which K? If after identifying it, simply we can apply the numerical processing to the original data to make it into linear in K. Okay, that's the calibration process. And then once we calibrate it, we can apply the rescaling or interpolation. This is essentially the resampling of the spectral signal into K space. Okay, it's a kind of the real operation to the data. Okay, did you understand the difference between the calibration and the rescaling? Maybe you can imagine that the calibration is required only once when you make the spectrometer or the system. Okay, once you calibrate it, this can stand for long. As far as you didn't touch the alignment of the spectrometer, it's always the same. But the rescaling is a rescaling of the acquired data, and the acquired data is surely different for each location of the sample, each A line, right? So this means the calibration required only once, but the rescaling should be done for every A scan independently. A scan is a spectral interference signal, one spectral interference signal. Okay, this one is a preparation process, and the rescaling is actually a measurement process. So maybe some of you, even me, code rescaling, the wide sense of the rescaling as it to include a calibration. Okay, and the reason is quite simple. Calibration is only once, and the rescaling we are going to apply always. The calibration is, in this perspective, time sense, it's only a small portion. It's very important, but a small portion. So we actually erroneously call all of them as a rescaling. But technically speaking, the calibration is calibration, and the rescaling is rescaling. Okay, and then if we didn't apply the rescaling, what's going to be happening? Here it's an example of a very old paper, a seminar paper of Maciej Wojtkowski, Journal of Biomedical Optics. So this is kind of official first demonstration of the rescaling of the spectral domain OCT. Okay, here is dashed line is OCT signal with rescaling. Okay, and here is the depth. On that time, he called it as tau, and I'll call it as harmonics. But it's the Fourier on it's an axis after the Fourier transform, meaning the depth. Okay, and if the signal is close to zero, this dashed line is a signal Fourier transform signal after rescaling, and this solid line is the signal without rescaling. Okay, if the signal is close to zero, it's still narrow. It's not sufficiently but narrow. Okay, but when the signal walks off from the zero, it becomes broader and broader. Okay, that's the point of the rescaling. So the rescaling is not that say fantastic, or doesn't have a high impact if the signal is close to 0 point. Means if the original interference signal has a low frequency. Okay, but if the signal goes to deep direction, the deep position, the frequency of the original signal becomes high, and then rescaling started to have a high impact. Okay, and maybe it's quite imaginable. When the signal has an extremely low frequency, like 0, it's just a DC, right? It's just a DC signal. In this case, no matter or nowhere you sampled the signal, it's just DC. So the rescaling should do nothing. But as the frequency becomes high and high, very small shift or very small skew result in a high phase distortion. Okay, the signal is just like this kind of very high frequency, and if you have the sampling error of like this, it becomes pi or 2 pi error. Okay, so this means that anyway, the point of this discussion is the impact of the rescaling is high if the signal has a high frequency in K domain. Means it has a higher impact if the signal in deeper position or farther position from the 0 delay. Okay, and the same thing can be confirmed by the swept source OCD. And again, this is kind of my old paper. Okay, on the blue is a signal with rescaling, and the red is signal without rescaling, OCD signal. And if the signal is close to 0, and even at the 0 delay, there is no difference between a rescaled or a non-rescaled data. But as the signal going farther and farther from 0 delay, okay, the sharpness of rescaled signal is not that much degraded, but the sharpness of non-rescaled signal dramatically decreased. And in proportion, the signal strength becomes low. Okay, so that's actually the problem we would like to solve. Okay, then let me dig into more detail of the rescaling process. And of course, calibration. What we can do for the calibration, and actually there are several methods for the calibration, but my group in University of Tsukuba made some special method of the calibration specialized for the OCD. Okay, the calibration of the spectrometer for OCD has some special requirement and also some special non-requirement. Okay, assume you are working for the company, they are manufacturing the spectrometer. When you ship it, you want to calibrate it. What would you need? You need to clearly identify which pixel corresponds to which wavelength exactly. Okay, like a 810 nanometer and a 811 nanometer have total difference. You need to carefully identify the absolute wavelength for absolute K. Okay, but in a case of OCD, the absolute wavelength is not necessary. What we need is only the linearity. Okay, that's actually the very important point. So we need a clear linearity of the spectrometer, and the requirement is quite high. Otherwise, the signal becomes broad in a region farther from zero delay. But for the if the spectrometer is used for the spectrometry, for example, this kind of linearity is not that important. Surely this is important, but the requirement is lower than that of OCT. Okay, it's a kind of accuracy issue. For a standard spectrometer calibration, we need an absolute number or absolute values of the spectrum at the wavelength. But the linearity requirement is it's high, but not as high as that of OCT. And in a case of OCT calibration, we don't need the absolute value of the wavelength, but the linearity requirement is quite high. Okay, so then what we can do, and actually we built or we designed the interference and fringe analysis method for the spectrometer calibration or sweep source calibration. It's the same actually. So then what we did, we put a mirror as a sample in the OCT system and detected the OCT signal. So here in this example, I've used the sweep source OCT, so there is no offset here. But anyway, you can assume we just extracted the cosine term. Okay, here is a cosine signal, but it's not real cosine. It's distorted because of the non-linearity of the spectrometer. The non-linearity of the spectrometer to K, or a non-linearity of the wavelength scan of the sweep source. Okay, then we would like to make it into linear in K, but before this, we would like to identify where is the sampling points which are linear in K. Okay, that's the calibration. So what we can do, the first, this signal is expressed as by this equation, it's cosine. Okay, cosine K of 2gm. And it's going to be split into two terms. It's an Euler's equation, right? Euler's formula, two exponentials. Okay, and here I write it as K, but in reality, in this case, the K is a function of the pixel position P. K is actually not a variable, but it's function already. That's the problem. I'm going to back to the mathematics again later. Okay, then Fourier transform it. We are going to have this signal. This guy is we call it the mirror signal or ghost signal or coherent artifact. It's something like a flip version of the OCT. And if you have some experience with the Fourier domain OCT already, maybe you've already seen it. There is an OCT signal, but there is a signal or image which is mirrored from this. Okay, and this guy is a remaining cell interference of reference to reference and probe to probe interference. Okay, and it is actually, okay, let me go back. It is actually these two terms. Okay, normally we apply the signal processing to remove these two, but surely there is some remnant of this. This. Okay, but anyway, this is not significant for this discussion. And the third one, this one, is the OCT signal of the mirror. Okay, and the mirror reflection should be quite narrow in OCT. Should be quite narrow in OCT. But because of the non-linearity of the pixel spacing to K, the signal is broadened like this. Okay, it should be like delta function we expected, but it's not because of lack of K linearity. Okay, that is something we would like to correct. And then what's going to be happening? What we should do? Clip numerically only this signal and Fourier transform it back to the original domain. And then applying the phase unwrap and see the complex signal. Okay, so now the signal becomes complex. And we have the amplitude or envelope of the signal, the amplitude of the complex signal and the phase. Okay, so then what is? So this signal corresponds to this term of cosine. Okay, so this means it's a complex signal. And I just omitted in this equation about the envelope, but this one is a spectral envelope. And then the phase is actually this guy. Okay, and in this equation, we didn't think about the nonlinearity. So it's linear in K. But in reality, this K, this term is not linear in K. So it's skewed. And that's the reason why this phase is not a linear phase, but they say bend, warped, right? So then what we need to do is remap the data like a right to left, or something like this. For each data would be shifted a bit, and then to make this phase into linear. That's the rescaling. Okay. The point is now we have this phase term. It should correspond this, but in practice, this is not a linear signal. So we would like to say shift each data point a bit to make the phase into linear. That's something we would like to do. That's the calibration part. And let me explain a bit more details of this with mathematics. Okay, the spectral interference signal, I brought it as the function of K here, can be elaborated like this. Now I've introduced the variable of P, the pixel index of the spectrometer. Okay, it's a pixel position. You can assume it as a pixel position. And A is a constant, and the gamma absolute Z0 is I'm going to skip the details of it, but it's an envelope. And I draw it with a red curve here. Okay. So here the envelope, some function, some slowly varying function. It's not that much important in this discussion. Okay. And then this one is again the constant IRP, the reference power and probe power. Combination of all of them are the envelope or amplitude. And then we have the cosine term. Okay, and this cosine term is of our interest. A slowly varying envelope or amplitude and a cosine. Okay, slowly varying envelope is a red curve. And the phase in a cosine is this green guy. And what we would like to do is first obtain this, means this guy, right? And once we can obtain it, we can have something like a remapping function to make it linear. Okay, now we are going to the direction to find out this equation from the numerical data. Okay, then what's going to be what we should do? As I've already explained, the first thing we are going to do is a Fourier transform of this numerical signal. Okay, then we are going to have these signals. The first one is the envelope or amplitude. So let's forget about it for now. And then the cosine term is going to be split into two portions, two exponential functions. Okay, it's an Euler's equation. and then Fourier transform, split into two exponential terms, and each of them a Fourier transform. Since the Fourier transform is a linear transform, the Fourier transform of the summation of two functions is a summation of Fourier transform of each function. Okay. So then we just applied it, and FT represents the Fourier transform. Okay, and then this one is an exponential function, one Euler portion of this cosine term, and it's Fourier transform. And then this is convolved with a delta function. Okay, and this delta function, hold on, it is strange. Sorry. And then this delta function, maybe I need to explain this one part. Okay, so here it's k. Okay, let me explain from the beginning for this part. So here is a cosine term. Okay, and the difference from this model to this model is now cosine term is a k. Sorry, the k in the cosine term is a function of t. That is something we would like to correct. Okay, and then this this one is not a k of t, but a k of p. Okay, k of p is modeled. Maybe I will correct it now. Hold on. Okay, K of B is now modeled as a summation of the linear part, which is linear to P, and the nonlinear part, nonlinear to P, I mean. Okay, and the linear part is not a problem. If we have only a linear part of this, the calibration is nearly done, or even we don't need a rescaling, right? But there is surely a nonlinear part. That is something we would like to correct. And then plug in this to this cosine term. Cosine term, plug in this to this cosine term and a Fourier transform. Okay, and then since it's a summation, the exponential the exponential I k1p plus k omega t is going to be split into two exponentials, right? The multiplication of two exponentials. And then the first one is a linear term, exponential term in which linear in t, this one, right? The Fourier transform becomes delta function, the shift theorem of OCD of Fourier transform. Okay, and then the nonlinear part is like this, and we don't have an analytic solution of the Fourier transform of this. So I just kept it. I have just kept it as a Fourier transform exponential blah blah blah. Okay, and originally this function and this function was in the original domain. It's a multiplication. So after Fourier transform it, the multiplication becomes convolution, right? It's a convolution theory. So now it's a convolution of two signals. One is a Fourier transform, it's a nonlinear term, and the other is a delta function. Okay. And by the way, the convolution with the delta function is shift. Okay. So this means this signal is shifted into this position. By the way, mu is a Fourier pair, Fourier conjugate of, okay, sorry, not T, but a P. Okay, So this one is a first term of within this cosine term. It's an Euler's first term. And the second term is like this. Okay, and it is nearly the same, but a complex conjugate. And also the shifted direction is opposite. So here it's the minus mu minus 2z0k1 means it's shifted into the positive direction. Okay, if this mu becomes positive, they are going to cancel each other and finally become 0. It means if this is minus, it's a shift to the positive direction. And similarly, if this is flat, if this is positive, the shift direction is negative. Okay. So this means actually this signal corresponds to the previous one, this guy. Okay, shifted to the positive direction and broad. And this broadening is this shift amount is defined by the linear term, and this broadening is defined by the nonlinear term. Okay. So here the shift, this part defines the shift, and this part defines the broadening of the signal. And then, we just crop only this part. This cropping is quite easy because this part and this part are shifted in the opposite direction. So we simply can apply the numerical window function. Crop only this means applying the function which is 1. Applying means multiply the function which has value of 1 only at around this portion, but for the others it is 0. Okay, this term is going to become 0 by multiplying it with this kind of numerical window function. Okay, then inversely Fourier transform. The inverse Fourier transform. Okay, then we have this signal now. It's quite similar to the original signal, but it no longer is cosine, but exponential. Okay, so then it's quite similar, but if this is cosine, it is not possible to extract this information from the numerical data. It's just a kind of oscillation, right? So analytically, we know analytically it can be expressed like this, that from the numerical data, we cannot extract this information. But once it became the complex signal, numerical complex signal, we actually simply can compute the phase of this complex signal. If you're using Python or MATLAB, simply you can use the function of, is it angle or something? Maybe it's depend on the language. So there is a numerical function to extract the phase of the complex signal. Okay, and or more primitively, you can use arctangent of the real and of the ratio of the real and the imaginary parts. Okay, so once you have a numerical signal of the complex signal, it's quite easy to compute a phase. And that computed phase is actually the inside of this exponential means identical to the phase of the cosine function. Okay, now we have this guy numerically, and analytically, we treat it as a phi m of t. Okay, now we have this one as data, and set it or denote it as phi m of t. And rewrite the equation to express k of t, right? Just shift. Sorry, maybe again this one is not correct. I is outside of this equation now. Okay, and then move these two terms into this term, and we have this equation, right? K of t equals 1 over 2z0 phi m of t. Okay, and phi m of t was numerically obtained. We already have this as a data, and I set it as k of t. And then P, analytically, we model it as a polynomial function, multi-order polynomial function. And I plug in this to these guys. Okay, then solve the equation numerically. It's just a fitting, actually, regression, numerical regression. And mathematically, it is a little bit elaborated, but simple. But in a programming, actually, it's quite easy. You can find a proper, say, off-the-shelf algorithm or the function in any language, like a Python, MATLAB, LabVIEW. You can find only a single VI or single the function. You can Google it, and a lot of documentation. It's quite easy. It's a single liner, one line. You can do this fitting. And then once you identify this coefficient, K0 to K3 or more, simply you can identify that each pixel has which K. Okay, by this equation, you can identify the relationship between the P and K. Okay. Okay, the end of the calibration part. So there are a lot of implementation details of this. But if you're interested in, you can check these papers, for example. So there are a lot of implementation details, but the important point here is understand the basic direction. And once you understood it, it's quite easy to read these papers. And like a Yasuno 2005 is a basic description of this method, and it's exactly the same what I explained today. And Makita 2008 is a modified version. It is for the case if the interferometer has a strong, if this is for the case the interferometer has a strong dispersion. So it first correct the dispersion and then applying this algorithm to find out the proper rescaling parameter. So my original algorithm I described here is suffered by the dispersion. If the interferometer has a strong dispersion, the calibration parameter cannot be that much accurate. And this is actually okay for 1.3 strips of OCD, for example. The optical fiber for 1.3 micron has nearly no dispersion. It's a non-dispersion region, 1.3 microns, especially for the optical fiber SMF28. But for 830 nanometers, 1.05 microns, and the optical fiber has a significant dispersion. So in this case, we need to take care of the dispersion issues. And if you're interested in, you can consult with Makita 2008. Okay. Then now we calibrated, then the rescaling. As I've explained, the calibration is only once, but the rescaling is for all of the data, the real measurement data. Okay. So this means by scanning on a sample, we are going to have a spectral interference screen at each point of the sample. Okay, this is linear in wavelength or nonlinear. The linear in wavelength or nonlinear, or linear in a nonlinear scanning function of the spectral. Okay, sorry, forget about the spectral. It's a linear in wavelength, but not linear in K. That's the problem. Okay, then we've already calculated. So we would like to remap the obtained data as it to be linear to K. So what we can do, there are several options like a linear interpolation and zero filling. And I'm going to talk about linear interpolation and zero filling today. And then the signal can become a linear in K, and applying the Fourier transform, and we have sharp OCT signal. Okay, then what we need to do, or what we can do, the linear interpolation is one of the easiest and fast method for the rescaling. Okay, assume these blue lines are the sampling point on a CCD camera. Okay, and there is some say interference here, and we are going to capture the data at this point. Okay, then the signal becomes something like this. This is something we can obtain, the raw signal. These blue lines are the sampling point, new sampling point, or should be new sampling point, which is linear in K. Okay, the green dots are the data we already have. And then we would like to guess the data at these blue sampling points. What we can do, the linear interpolation is the easiest way. Quite easy. So there are 2 points, right? And then draw the line, linear line, and then take the point, this line intersect this sampling point as a new sampling point. Okay, so here is another example. Here is a line, linear line we draw from these 2 sampling points, original sampling point. And what we would like to know is the data value at this point. So we just take it as a new sampling data. It's easy, right? And I wrote some equation that actually it's a junior high school problem. Okay, you can check this equation carefully, and you can find it. It's a junior high school problem. It just looks like a bit elaborate. Okay, and this one is a linear interpolation. It's the easiest way. But linear interpolation has a significant problem. Its passband is quite narrow. Sorry, the passband is quite narrow. It is mathematically proven. Okay. Assume in general, there is a data sampled with particular frequency. Okay, the sampling frequency. So in this case, the maximum highest frequency this kind of signal carry is a half the sampling frequency, the Nyquist theorem, right? That's the theoretical maximum. The Nyquist frequency is the theoretical maximum we can obtain with the sample data. But all of the local interpolation, including this linear interpolation, is known to have the maximum passband of half the Nyquist frequency. Okay, that's a problem. So this means when you apply this kind of local interpolation to the OCD signal, actually this is quite fast in a computation. But the maximum frequency becomes half. Means when you are applying with the OCD, the signal rapidly decays if it further, if it going to a deep region, which is deeper than the half of the measurement range. Okay, that the most deep point in the measurement range is actually the Nyquist, right? But the passband of this kind of algorithm is the half of the Nyquist, the middle point of the measurement range. So this means after the middle point of the measurement range, the signal is rapidly decayed, or in my experience, actually, the signal is not that much decayed, but the signal flow and the noise floor becomes elevated. Maybe some of you already have seen the signal in a deep region. The signal is accompanied with something like a significant high side lobe, right? Like a trapezium, like a side lobe, and the signal started to bury in this side lobe. This is the effect of the linear interpolation. Okay, that's the problem of the linear interpolation. So then the next question is how we can solve it. It's a combination of the zero filling, spectral interpolation with zero filling. Okay, zero filling is a method to increase the sampling frequency or sampling points. Okay, by increasing the density, the zero filling is a more better way of expression. Zero filling is a method to increase the sampling density of the data after the acquisition. And once we make the original data density into double, the Nyquist frequency becomes double, right? And then applying the linear interpolation. And the frequency, the maximum frequency becomes half. Then it's a Nyquist, original Nyquist frequency. The first make it double, and after make it into half. That's the point. Okay, then how we can then the next question is how we can make the data density double. It's a zero term. Okay, the operation itself is quite simple. The Fourier transform the signal, and you are going to have like this kind of signal, right? Here is a zero frequency, and here is a positive frequency and negative frequency. Okay, then put pseudo zero data here. Fill some portion of the data with zero. Okay, so it means the sampling data points becomes double or the 4 times or even more, and then Fourier transform it back. Okay, the Fourier transform and sorry, the range of the Fourier spectrum is defined by the sampling density in this original domain. So this operation is just put the data, extrapolate the data here. Means that the sampling, the spectral range after the Fourier transform is the same with the zero filling. But a data number becomes double or more, meaning the data density becomes high, like this. Okay, once you make, say, for example, the original data has a 248 pixels, and then put another 248 zeros here, and it becomes the data density after the Fourier transform it back into the original domain becomes double. Okay, 496. Okay, so these greens are original data point, but by applying this operation, we are going to have these data points. Okay, it looks similar to the linear interpolation, but this is not the local interpolation. The Fourier transform has a Fourier transform uncertainty. One point in the original domain are broadened or the spread into the whole domain after the Fourier transform. And the whole domain in the Fourier transform can affect to each point of the signal. The local and the global is split by the Fourier transform. And we do the extrapolation in the Fourier domain means we did the global information to do this resampling. Okay, that's the point of zero filling. It's like a magic. After taking the Nyquist frequency, after taking the data, we can increase the Nyquist frequency infinitely. Strange, right? So then, okay, it's some additional point. So then, how does this kind of magic happens? We just added the information. Where we extracted this information. That is, when I was a student, I learned this method, and I was quite skeptic for this at the first time. There is no information. It should be something wrong. But in reality, it's not. So then, what's the point? Actually, we used a priori knowledge of there is no high frequency signal. Means this portion is zero. Okay? Got it? So this means if we, in reality, if we have some high frequency signal, but we couldn't detect it, the zero filling fails. But in the case of OCD, fortunately, this won't happen most of the cases. So you can safely use this zero filling. So don't forget, the zero filling is fantastic, but it uses a tacit assumption there is no high frequency signal. We use this a priori knowledge to extrapolate the spectrum And after the Fourier transform the signal back into the original domain, this extrapolation becomes the interpolation. Okay, so so far, sorry. And then the point is again, and after doing the developing, you can apply the linear interpolation or a little bit more better interpolation, even like a cubic spline. And then you have the K-linear signal. And that's normally we have been done for the spectral domain OCT. Okay, then some additional tricks for the rescaling. For the spectral domain OCT, we have no other choice. There are several choices for the algorithms, but we have no other choice but doing a numerical rescaling. Sorry, and technically there is some example of the K-linear spectrometer or something, but please forget about it. If you're interested in, you can Google it. Google Starlight, technically. Okay. But there is some other trick for, especially for swept source OCT. It's a hardware rescaling. Means actually, it's not the rescaling. Hold on. Cooper, 2005. Yes, it's a hardware, totally hardware rescaling. It's a we call it as a cake blocker. The spectral domain, in the case of spectral domain OCT, we first obtain a lambda linear signal and then remapped it into K-linear by using a numerical tree, right? But in the case of swept source OCT, we can do additional trick by which from the beginning, we can acquire a K-linear signal. That's K-clocking. For the K-clocking, what we need is an additional interferometer. It's here, right? It's a Magenta Interferometer. And since it's a swept source OCT, by time, it scans the wavelength. But this is not linear in K. Right? By scanning the wavelength of the light source, we are going to have cosine, the oscillation signal from this interferometer. Okay, it's not linear in K if you detect it in a time equivalent manner. But this oscillation signal is just like the signal I've shown here, maybe here, this guy. Okay, so this means if we can digitize the signal, the OCT signal, OCT interference signal, with the same timing when this cosine signal becomes peak or valley, the detected signal is already linear in K. Okay, like this, it is distorted, right? But if we can take the signal at the timing of each top or peak of this signal, using this signal to trigger the data acquisition of each data acquisition, and then taking the signal from this real OCT interferometer. Okay, so if we can do it, actually the signal detected directly from the DAQ is already linear in K. That's K-clocking. And technically, what we use is not the peak or valley, but a zero crossing. So here it's zero here, and we just check when the signal crossed the zero voltage. Okay, but it's a kind of implementation details. And for the high-speed data acquisition, only a limited solution for the K-clocking, DAQ, the data acquisition. It's the requirement of the data acquisition board is quite high for this K-clocking. Okay, and in our case, we are normally using Alazate. That's something that recently I talked that we need to we need to make the Alazate module for our new measurement framework, blah blah blah. That's the reason why I'm still sticking with Alazate. And NI recently released something like OCD compatible of K-clocking, OCD and K-clocking compatible DAQ. Not the function generator, the data acquisition card. Okay. So, and then this one is the first demonstration of the K-clocking done by Robert Hoover, 2005. And currently, nearly almost all of the sweeping sweep laser has its built-in K-clock. And actually, also we are using it in our system, right? That the K-clock. And in this case, the light source itself possesses the Magenta interferometer inside and generate the K-clock. And what we need is just plug the SMA cable, electrical cable to the light source, and we can obtain the K-clock. That's easy. But sometimes we need to, if we are interested in a higher frequency of the K-clock, sometimes we need to build a Magenta interferometer by ourselves. Or in our trick, we are using an RF frequency doubler to have a higher frequency, make it as a double the frequency, and it results in a deeper the measurement range. Okay. Okay, then let's go to a short but the second half of this lecture, the interferometers of OCD. Okay, maybe I'm going to put some chapter mark here. Have a pause. Okay, we are going to go to the second half of today's lecture. It's the interferometers of OCD. Okay, it's just a collection of the interferometers. It's been used. They've been used for the OCD. Just first, I just give say something like a catalog classification of the interferometers, and I will give you the selection chart of the OCD interferometer. Okay, the one of the first and quite typical interferometer of the OCD is unbalanced microphone interferometer. Okay, and it maybe when you think or when you started to think about an interferometer, the first interferometer you can think of is a microphone. It split the beam into two, and actually it's been rigorously used in my schematic in this lecture. Okay, the light is coming here and split into two, and reflect back at the probe beam and the reference beam, and then couple it again with the same coupler, or if it is a bulk optics, it's a beam splitter, right? And then introduce into the detector. In the case of spectral domain OCD, it's a say spectrometer. In the case of time domain, it's a photodetector. Okay, this one is a standard microphone interferometer. Light is split into two, and I take the same path to recombine, and then send it to the detector. Okay, then next interferometer, major interferometer. It's a Magenta interferometer. I've already used this word to explain about a K-clock. Right? The Magenta interferometer is typically used by the sweep source. Okay, let's see. Forget about this part. It's it's a trigger generator. And interferometer starts from here. Okay, the first, the beam is split into two, and the one path is for probe, the reflected back or scattered back from the sample, and then going to this circulator, the new device. I mean, new in this lecture. The classical device, but a new in this lecture. Okay, the beam is split into two, and one is scattered back, and then going to the circulator. And what is this circulator? What the circulator is? It circulates a beam one directionally. Okay, if the beam is coming from this side, 100%, ideally 100% of the light is going to this direction. Okay, and if the beam is coming back from this direction, it's not going to this, but 100% ideally of them are going to lead to this direction. Okay, coming from here to here, and then once it comes back, from here to here. It's a little bit like a magic. But you can Google it. But a trick is a polarization. By using a polarization and its rotation, we can achieve this kind of unsymmetric path. Okay, but anyway, it's quite light efficient. So in this case, for example, in this example, on the 90% portion of the light from the light source or the interferometer is led to the sample, and then 100% of this 90% is collected by this. Okay, and for the reference arm, again, the 10% portion is reflected by the mirror, and 100% of them are collected. And then coupled, these two beams are combined again with another coupler here, 50-50. And one interference signal is led to this photodetector, and the other is led to this photodetector. The balance the balance detection. Okay, and this is not exactly the topic of today, but I think I explained about it somewhere recently. But anyway, forget about it. You can check it, you can Google it if you're interested in. It's a little bit exceed today's talk. Sorry, maybe I've explained it in a student seminar, right? Okay, so by this coupling, we are going to have two interference signal here and here. And the interference phase is swapped pi, transit it into pi between these two signals. So if you can compute the interference signal of here, we can electrical subtract this signal from this. We can enhance the interference term, but we can remove the noise. It's a kind of a high sensitivity detection tree, dual balance photodetector. And actually, you can buy this kind of module in Thor Labs or several of the optical component companies. It's already a quite established technology. Okay, and then the signal is digitized by DAP. Okay, then again, let me recapitulate the point. Magenta interferometer, the reference beam and the probe beam takes a different path, a split and a combined with a different device. Okay, that's the Magenta interferometer. And we are going to have two interference signals and are used, and these two are detected and electrically subtracted. Okay, so then how we can select the balanced Michelson, unbalanced Michelson, and the balanced Magenta. Here, the spectral domain OCD, it's an example of the spectral domain OCD. As for the spectral domain OCD, we have a spectrometer, right? And this is not really compatible with the balance detection. We have only one line camera here, and making it double costs a lot. Okay, and in one hand, it costs a lot, and also there are lots of technical difficulties. Although we can do it, it's a lot like it. Okay, so normally for the spectral domain OCD, we have in practice only one choice of a single detection. And for the single detection, maybe the Michelson interferometer can be a good compromise. Okay, some portion of the light is going back to the light source, and actually it cut by the isolator anyway. Okay, but still, it is quite reasonable. For the swift source, we don't need a spectrometer. The spectral resolution is done by the swift source, light source itself. And what we need is a point photodetector. And for the point photodetector, it's quite easy to have a dual balance receiver or dual balance photodetector. So maybe the Magenta interferometer is a choice. In addition, for the spectral OCD, I'm going to talk about it in the next lecture. That for the spectral OCD has a quite high ring level in comparison to the spectral domain OCD because of the short exposure time, 1,000 times shorter, or 1,000, 2,000 times shorter exposure time than a spectral domain OCD. So we would like to reject the ring relative intensity noise. And for this, we need actually a dual balance photodetector. And for this, we need something like a Magenta interferometer. Okay, if you're working for the spectral domain OCD, maybe the choice is a Michelson interferometer. But if you're working with a swept source OCD, the primary choice is a Magenta. Okay. And then there is something similar or something in between that a typical unbalanced Michelson interferometer and the Magenta interferometer. We call it a balanced Michelson. without circulator. Okay, some people call it as still part of Magenta. But anyway, the name is not that much important. So here, the important point is here I denoted it as a balance mechanism. Okay, the light is coming from the light source and split into the probe. In this case, the probe is up and the reference down, right? And then these two beams is combined with another coupler here, 50-50. From this perspective, it looks like Magenta, right? But like a microphone, the beam from that sample is passing the same the coupler with the going path. Okay, so this coupler was used twice, but for the reference, it's a monodirection. It's coming from here and reflected back, taking other path to be led into 50-50 coupler. Okay, and the beam are combined with these two and balance for detected. Okay, this is actually typically used for the 1 micron strips of OCD. Why? It's something like a Magenta interferometer, but I have a slightly lower light efficiency. But it doesn't use the circulator. That's a practical point. Actually, the device performance of the circulator for 1 micron light is not as high as that of 1.3. So using the circulator for 1 micron is in a very early stage. It was quite expensive. It's a 10 times expensive more than that of 1.3. And in addition, the performance was low. And now we have, say, cheap, and actually it became cheap already, but still the performance is not as good as 1.3. So in this case, the choice can be the microphone interferometer, the balanced microphone interferometer. And this is typically used for the 1 micron swept source OCD. Like currently available, commercially available, the retinal swept source OCD. Most of them are using this balanced mechanism. Okay, and surely you can use the circulator for this. And but as I mentioned, one point, the good point is it has a quite good light efficiency. But in the other hand, the circulator is still a bit expensive, but actually the performance is not good. And I'm going to digging into that. I'm not going digging into the details of this point, but in general, it has a significant polarization mode dispersion, and the image is actually blurred, distorted, blurred. Sorry. Okay, so maybe, and even in my early paper of the 1 micron swept source OCT, maybe 2007, maybe I've used the circulator. But for the next version, after the next version, we banned that circulator and moved into that balanced microphone without circulator. Like the current system working in a clinic in our collaborators are based on the balanced microphone without circulator, for example. So this one, the balanced microphone with circulator is already a history. Okay, so then let me summarize the good point and the bad points of the interferometers. The Michelson, the first thing I would like to think about it, the Michelson versus Magenta interferometer. The Michelson interferometer is good because it doesn't require elaborate fiber components, namely circulator. Okay, but a bad point has a low probe efficiency. Okay, means hold on. The probe efficiency, I'm going to talk about it in the next slide. And it is typically used for 830 nanometer swept source OCT, spectral domain OCT. And then the Magenta interferometer, at that point, it requires circulator, But a good point, it has a high probe efficiency. So if you use a proper circulator, the probe efficiency is quite high. Okay, all of the light reflected from the probe can be collected and can contribute to the OCD imaging. Okay, and another good point is it is suitable for balance for detection. So it further contribute to the high image quality by suppressing the ring relative intensity noise. Okay, and it is particularly suitable for 1.3 micron swept source OCD. And for the 1.0 micron swept source OCD, as I mentioned, normally we are going to use that balanced microphone interferometer. Okay. The probe efficiency issue. Okay, I just briefly mentioned about it in the last slide. Assume the coupling ratio or splitting ratio of the coupler as A to B as a probe to reference. The probing efficiency means the probe power, the portion of the probe power which is used for the imaging in comparison to the input to the interferometer. Okay, as I think the basement is the input power of the interferometer. Okay, and the final point is that the light power which can be led into the detector. Okay, by thinking about this efficiency, for the unbalanced microsound interferometer, it becomes like this: AB divided by A plus B squared. And this means if this is a 1-to-1, the maximum 25% for the 50-50 coupler. It's quite easy, right? The light is coming to the interferometer and split into 50% and 50%, 0.5 and 0.5. And this 0.5, assume, can be all of them are reflected back from the sample and then going back to the coupler again. And again, half the portion is gone by this coupler. So it's a 0.5 times 0.5, 0.25, 25%. It's the maximum we can use for the imaging. And for the Magenta interferometer, the probing efficiency is A divided by A plus B. Okay, so the beam is split into probe and reference. And then once it was transferred for the probe, all of the signal can be contributed to the imaging because of thanks to the circulator. Okay, so in this case, for example, the efficiency can be like 99%. Means for the first coupler, you can use a 1% portion of the reference and a 99% for the probe. And in general, the requirement of the reference power is low. So we can use actually the 99-to-1 coupler or 9-to-1 coupler, 90% coupler or something. Okay, so the Magenta interferometer, the probe efficiency is quite high. And the balanced microphone is actually the same efficiency with the unbalanced microphone. The maximum 25% with a 50-50 coupler. Okay. Then finally the selection chart. By considering or accounting for all of the points, we can I can give a quite simple selection chart of the interferometers. Okay. So first, aware which kind of OCD system you want to use: SD or swept source, spectral domain or swept source. Okay. And normally, this selection can be done by the wavelength you want to use. If it's 840, it might be spectral domain, SD. And if it's 1 micron or 1.3, typically your selection can be swept source. And the selection of the wavelength, it depends on the sample or resolution you want to have. Okay, and if you're interested in, please check my online material. I mean, the textbook tutorial of OCD. But anyway, once you decide to define what you want to measure and what the resolution you want to have, you can select the wavelength. And once you select the wavelength, you can select whether you're going to use the spectral domain or swept source. Okay, and then if you are going to use a spectral domain, you have only one choice: unbalanced Michelson. Okay, you don't need to worry about it. Select the unbalanced Michelson. And if you are going to use a swept source, then you can consider the output power of the light source. And if it is high, sufficient light source, maybe you can use a balanced Michelson without circulator. Okay, because the balanced Michelson without circulator have a little bit low efficiency, but the setup itself is simple. We don't need a circulator. Okay, but a light source output power is low. You need to use the light efficiently. Okay, then check the wavelength. If it is 1.3, actually the circulator is cheap and have a good performance. So you can use a balanced Magenta interferometer. And if you're going to use 1 micron, you need to think about it, whether you need a high efficiency of the probe. Okay, it's another idea, efficiency of the probe. It is particularly important for the eye. Means if there is a safety limit of the illumination, you need a high efficiency. Okay, the probe efficiency, what I've talked, is a multiplication of the going loss and backward loss, forward loss and backward loss. But to have a high probe efficiency, I mean the collection efficiency, the important part, the efficiency for the backward part. Okay, illuminate the sample with a weak light and as much of the reflected light we would like to obtain. Okay, so if there is no safety limit, simply you can use the illuminate the light, illuminate the sample with the high power and collect a small portion of it. For the other side, both of them are the same. But if the sample is well damaged by the light, we need to illuminate the sample with a weak light, and we need to recouple, or we need to capture the reflected beam with high efficiency. And actually, the retina or the eye in this case. So if you need a high efficiency, like eye, your choice is balanced Michelson with circulator. Okay, and if it's not, maybe also you can consider balanced Michelson without circulator. Okay, but recently, after making this material, the circulator of 1 micron has a lot of problems. We found it. And even for the eye, normally the selection is this one. Maybe I need to revive this material. In practice, normally we are using now the balanced Michelson without circulator, even for the eye. Okay, because of the strong and polarization or dispersion of the circulator. Okay. So then there are some extra issues. Maybe I just give it in a few minutes. Okay, so today's talk is about the implementation of the OCD. And I've talked two major issues of the implementation. And just a small, maybe 1, 2 slide. Yeah, one slide, the last slide of today's lecture. The extra issues for the practice. If you're working for the OCD, maybe it's better to know about it. First point is a fibratic shape. And actually, this material was originally made for the lecture in the industry guys to manufacture the OCD. So it's very practical. But when you make the OCD, and first, the interferometer, the fiber of the interferometer should be single mode. Okay, if you use the multi-mode fiber, you are going to have a mode dispersion, and it distorts the image. So you need to use a single mode. And for the single mode fiber, there are several types of the fibratic configuration. And for the OCT, typically we use FC-APC. APC, PC is for physical contact, and A is angled physical contact. in the fiber tip, and when you connect the fiber, two fibers, it's a physical contact. Okay, it's a PC, and angled. It's angled with 8 degrees. By this, we can suppress the reflection at the interface. There is a reflection, but it cannot propagate back. So we can forget about the noise from this. And since OCD has a very high sensitivity, if we have a very small light reflected at the tip, it creates the ghost signals. So we would like to avoid it. So it's APC is masked. And FC is a standard for how we can connect the physical connection of the fiber. FC is a screwing, and like SMA is a switch. Okay, but typically we are going to use FC APC, and APC is masked, and FC is recommended. It's a combination of the two standards, FC APC. So like in our lab, nearly 100% of the fiber tip are FC APC. Okay. If when you make a when you buy some components, fiber components for the OCD, simply you can use FCAPC. You need to select the option actually when you order it, but you can select FCAPC. And then excess loss in fiber interferometer. The recoupling loss at a fiber tip is around minus 2.2 dB, typical, 60%. Okay, you should take it into account. Means that when you extract the light from the fiber tip and put it into bulk optics and put a mirror on it and recouple it into the single mode fiber. And actually the coupling efficiency is not that high. Maybe you are going to lose the 40% portion of the light only by extracting the light and going back to the fiber tip. Okay, that is 60%. And in dB is minus 2.2 dBs. And when you use a direct fiber attachment, like a FCAPC, the loss is something like a 0.1 dB. I wrote it 3 dB, but maybe this is not. I think I can remove it, or maybe 0.3. Okay, if you have a 3 dB loss in a fiber attachment, there is something wrong with your system. Maybe the fiber tip is damaged, and it can be very frequently happen. Okay. And the circulator efficiency is for 1.3, it's high, but for 1 micron, it's not high. It's around minus 1.2 dB to minus 1.4 dB for single pass. Okay, and the coupler, 2020 coupler, and a 50-50 coupler has a loss in principle of minus 3 dB, right? The half. So this means there is not that much high difference with the circulator and the coupler. So that's the reason why normally these days we use an balanced Michelson without circulator for the 1 micron surface OCD. Okay, it's another thing you need to think about. And also polarization mode dispersion, the circulator at 1 micron is high, actually a few 10 microns. Means when you put it pretty much depends on circulator, and these days there is a good circulator, but in general, relatively it's high. And a few 10 micron means if you put a light with a 2 instant polarization into the circulator, the one polarization state delays for a few 10 microns after passing the circulator. Okay, circulator has its own polarization axis, eigenpolarization axis, and eigenpolarization, yeah, axis of eigenpolarization. Okay, and between these two axes, the light is delayed, mutually delayed, and it's significant. So when you use a circulator with 1 micron, it might be better to first clean up the polarization into single state and align it into one of the eigenpolarization state of the circulator. So in this case, the delay is just absolute delay, the relative delay, and there is no reference. So in this case, you can forget about the PMD. But actually, you need a frequent alignment for this. So I don't recommend, to be honest, I don't recommend to use a circulator for the 1 micron. Okay, so that the end of today's content. Do you guys have some questions or something you want to clarify more, a bit more? Fine. Okay, so the next time of the lecture would be a little bit more property, the theoretical point of the OCT about the resolution and sensitivity. Okay, and please expect some interesting lecture again. Okay, so that's the end of today's lecture, and thank you guys, and thank you very much for all of you guys.